My name is Sudeep Dasari, and I'm presenting Transformers for One-Shot Imitation. This is joint work with Abhinav Gupta. Humans can easily visually imitate. For example, if you saw someone stacking blocks on top of each other, you could perform the same task yourself. Can we teach robots to do the same? Specifically, what sort of visual representations are needed to do this? For training, our approach assumes access to hundreds of robot trajectories and teacher videos grouped by semantically meaningful tasks. Note that the human and robot environments do not need to exactly match. During test time, the robot should perform new tasks after observing the human. For this to work, it must generalize to new situations unseen during training. This project seeks to learn a good visual representation for this problem. We hypothesize that a good embedding for one-shot imitation should use video to focus on relevant details, like the purple block in this example below. Finally, the embedding should encode relevant dynamics informations. But what's the right way to implement such a representation? Inspired by recent successes in NLP and vision, we choose the attention-driven transformers method instead of a more traditional MLP or LSTM. Image frames from the agent and demonstrator are passed through a pre-trained ResNet 18 network, and then further processing is applied using a transformers network. The final output is a per-frame embedding which ideally filters out irrelevant information thanks to the attention mechanism. What losses should we use to supervise this? Since we have optimal actions, a behavior cloning loss is an obvious choice. However, behavior cloning alone may not encode all relevant details into the embedding. So to ensure that the representation preserves dynamics information, an inverse model loss predicts in-between actions from subsequent representations. And finally, we add an optional point loss which predicts 2D pixel locations of the target agent's end effector in the future. Our method is experimentally evaluated in simulation. We create Majoko environments with 16 tasks corresponding to taking each object to a separate bin. The environment is duplicated to support two robots. The red Sawyer robot on the left acts as the teacher, and the white Panda robot acts as the target agent. A dataset of 1,600 demonstrations is collected to test our method. We train our method alongside 3 baselines on the simulated dataset. For reporting purposes, task success is reported on stages of the pick and place task. After all, in order to place an object in the right bin, the robot must reach and pick it first. Our method performs substantially better than all the baselines on all stages. This is especially impressive since it beats the auxiliary meta-learning model, which makes assumptions about the tasks. Here we show a qualitative example of placing the Coke can in the back right bin. All 3 models are able to work in this instance. In this instance, however, the LSTM model incorrectly reaches for the wrong object. And finally here, only our model can successfully bring the brown block to the right bin. The meta-learning model fails completely, whereas the LSTM again does the wrong task. We now seek to understand if the transformers architecture improved test time performance. Various neural network policy architectures, including a version of our network without attention, are compared. Note that the transformers architecture performs best compared to all other choices. Finally, we investigate which parts of the method were the most useful. We train ablations of our model without the inverse loss, without the point loss, and without any data augmentation. This is compared against the base model when trained on datasets with varying amounts of data. Note that the model without the inverse loss performs significantly worse at control. This effect increases in importance as more data is used during training. Our experiments demonstrated that our transformer approach significantly outperforms prior work in visual one-shot learning tasks. In fact, the new approach can match baseline performance when trained on a third of the data points. The inverse control loss proved to be crucial to create dynamic aware embeddings that were suitable for control. Both facts support our hypothesis that context-driven and dynamics-aware embeddings are good for visual imitation tasks. Our approach did require a paired dataset, however, which could be limiting to make this work in more open domains. Future work should focus on lessening this burden by making use of unpaired data, or data with human videos but no robot demonstrations. Thank you.